Donna. Welcome to Related Rates. I'm very excited. I really like working these problems, and I hope you will too. All right. We are going to implicitly differentiate the following formulas with respect to time, and we're going to talk about what each of those rates means. So let's look at number one. That's the surface area of a sphere. You may not have known that. If we want to differentiate that thing with respect to time, remember how we've talked about if the variables don't match? Remember how if you had to do the derivative with respect to x of y squared, what did you do for your answer? 2y dy dx, right? It's the same idea because we are differentiating with respect to time, all right? So obviously we don't have t's in here, so we're going to have to implicitly differentiate. All right, so here's how it works. A equals 4 pi r squared. Now 4 pi is a constant, right? So you're going to treat it just like a number. The derivative of the left side, a, with respect to time is dA dt. And then notice on the right side we have got 4 pi times r squared. 8 pi r dr dt. This is the rate of change of the area with respect to time. This is the rate of change of the radius with respect to time. So when I'm taking the derivative of area with respect to time, it's dA dt. This,
Why does it not match the equation? Why wouldn't it be the same? Why doesn't it match the one that's in the equation? Why isn't that one dA dt?
Because I was taking the derivative of r. Yep, it's exactly like when we did the y. But when I'm taking the derivative of a, it's going to be dA dt. When I'm taking the derivative of r, it's going to be dr dt.
So on the other ones, like we just did that, like y and x as
Yep.
variables.
Yep.
Like why did we only multiply dy dx? Like on this one you multiplied it, like you made it for each variable. Why didn't we do that?
Because we did. Because the only two variables we had were x and y. And when you take the derivative of x with respect to x, it's just normal old taking a derivative. But taking the derivative of y with respect to x, I'm going to have a dy dx.
Okay.
Does that help any? Okay.
So you just did the derivative of both sides?
Yes, absolutely.
So any variable that's not next to the d on the bottom, you do the d.
Yes. Yes.
Like that variable.
Because I'm going to take the derivative of everything with respect to time. So yes, I will have to take the derivative of each variable with respect to t. Yes.
If it was not radius and it was like 4 pi t squared, then you wouldn't have that.
You won't have a t in these equations. It's not going to happen.
But like, if
But
that was what it was,
see, yes, correct,
wouldn't
correct.
have- okay.
Because see, what we're doing is we are trying to find a rate of change with respect to time. We're trying to find a rate of change of some unknown with respect to time. Go ahead, Mason.
So which variable do you solve for?
We'll get there. Let's look at number 2. The answer to that starts on page 2. Okay, the volume of a sphere, volume equals 4/3 pi r cubed. We're going to take the derivative of that function with respect to time. dv dt. Now hang on. Hang on. How do you take the derivative of r cubed? 3. Yep. So I wouldn't write this down, but I want you to take a look. There's the 4/3 pi, right? Times 3r squared dr dt. You with me? What's 4/3 times 3? So this is 4 pi r squared dr dt. Oh, wait, the derivative of the volume of a sphere is the surface area of a sphere.
What's the DR?
Sure. Yeah. Okay. Ah, because a volume is cubic and area is squared. So wouldn't that make sense that it would step down one? Okay. Now, A equals the square root of c squared minus b squared. Now, please pay attention. C is a constant. You are going to treat C as a number. What is the derivative of a number? 0. Please remember that as we work through this problem. A equals, and I'm just going to do a rewrite. What are our variables? No. B is a variable, and A is a variable. C is a number. C is a constant. So the only variables we have are A and B. So let's take the derivative. dA dt Oh, I forgot the dB. Yeah, I forgot the dB dt. Ah! Let me write smaller. Let me write smaller. Come on, Stennett, get with the program. dA dt equals 1/2 of c squared minus b squared to the negative 1/2 times the derivative of the inside, which is negative 2b dB dt. You mean to clean that up a little bit? We can. On a free response, I would tell you not to. Well, I'd probably tell you to get rid of the negative exponent. Yeah. So negative, here's what I would do. I would do it like this. Negative b over the square root of c squared minus b squared times dB dt. That's how I would write it. No, same thing. It'll just look like a complex fraction because you'd have a fraction inside a fraction.
But if you were to replace it with like, you know how we.
Yeah, and the answer, yes, and
Say the same.
it's fine, yeah. Now remember, one thing that we haven't been answering is what does each rate in the equation represent? Remember, all the dB dt means is the rate of change of b with respect to time. That's all it means. And the dA dt is the rate of change of a with respect to time. All right, let's look at number 4. Volume equals pi r squared h, where r is a constant. This is the volume of a cylinder. Now pay attention. What is constant? R. How many variables do we have then? V and H. Yep, just 2. So let's take the derivative of this thing with respect to time. dV dt equals R is a constant, so R squared is a constant.
So it would just be H or 1? 0.
What if it was this?
3. So it should be 1.
3 dH dt, right?
So it should be V. No, it should be H would be
Oh, well, what if you were taking the derivative of this with respect to time?
Yeah, it'd be 3.
It'd be 3 dH dt, right?
So
So what's this going to be?
this would be pi.
Yeah, pi r squared dH dt.
The derivative of constant is 0.
Well, it's a coefficient. It's the same, it's the same thing.
But
Yeah, the derivative of 3h is 3
Mhm.
times dh dt. So the derivative, pi r squared is a constant, so it's the constant dh dt. Yes.
But like in C, the equation above with the C, that was different because you're subtracting. But the constant
Correct,
is one of
correct.
the coefficient.
Yes.
Like an add.
Yes, you're right. I got it.
Right.
Okay. Cosine theta equals x over 15. I'm going to strongly encourage you to do a rewrite on these and rewrite that as 1/15 times x, or at least think it that way. Remember, we're taking the derivative with respect to time. How many variables? Theta and x. All right. Negative sine theta d theta dt, good, equals dx dt.
oh, that's weird.
Don't, Leibniz, that's Leibniz's notation. And it was not intended to be a fraction, but we can consider it like a fraction. However, do not split the dx and the dt up. For instance, don't put 1 dx over 15 dt. Leave the dx dt as a unit. Okay? Because the derivative of this with respect to t, remember, 1/15 is the coefficient. So if it had been 3x, the derivative of 3x is 3, right? So the derivative of 1/15 x is 1/15. But then since the variables don't match, I have to add on the dx dt. The d theta dt, the rate of change of theta with respect to t. Now, whenever you deal with a theta, hands are cold. Whenever you deal with a theta, that's going to be measured in radians. So your units will be radians per second or radians per minute. We will never use degrees in here, ever, ever. Volume of a cone. Now, how many variables do you have? Did it say anything was constant? No. So you do have 3 variables here. So how many d blanks dt's are we going to have? 3. Right. And yes, circle box. Why?
Oh. Because you have I don't
Because,
the peanut, right?
well, no, it's not a peanut. Yeah, I'm going to write pi over 3 times r squared h. All right? Are you okay that 1/3 times pi is pi over 3? So, what rule are we going to have to use to differentiate r squared h? Product rule, aka circle box. All right, here we go. dv dt pi over 3 times perfect 2r dr dt times that's perfect. Yes, because at this point you would be plugging in values. Emily? Are you stuck? get your highlighter. Now, Sparks has his way of teaching related rates. I do it a little bit differently. So I'm not going to really follow this part. I have 3 words that I use when I teach related rates. And I want you to write them down. Find, given, when.
Are we gonna be writing in the?
Are we going to be writing in those boxes? Not the first one probably, but some of them. But it will not have anything to do with the 1, 2, and 3 that I marked out over here. All right. I'm doing that. One reason I'm excited about it, and the other reason is my hands are cold. You're going to take your highlighter and you're going to highlight what's important. All right? Air is leaking out. That's important. Of an inflated balloon in the shape of a sphere at a rate of 230 cubic centimeters per minute. Now, so I'm thinking to myself, okay, self, what does that mean? Air is leaking out of an inflated balloon. What is changing? The volume at a rate of 230 pi cubic centimeters per minute. So is the volume increasing or decreasing? So I know dV dt, don't I? The rate of change of the volume. So we're just thinking, okay? We're just thinking as we go through this. Don't write anything down. Now, let's continue. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? Yeah, heck yeah. Okay, what are we trying to find?
The rate of change of the radius.
We're trying to find the rate of change of the radius. So find, what am I trying to find?
dr dt.
dr dt. I'm trying to find dr dt. Given, what am I given in the problem?
Radius is what?
I'm given dV dt. And what is dV dt?
230.
Negative 230 pi. When R is 4. Do you understand what we've written down so far? I know what I want to find, I know what I've been given, and I want to know the rate of change of that radius at this particular instant. Okay? Now, you're going to write an equation, which is almost always going to be a geometry formula or a trig equation that relates all the variables in the problem. I got the volume of a sphere. Well, from the front page, the volume, what's the volume of a sphere? What's the formula from the front page? Volume of a sphere. Now, I want you to look, starting right here, it says substitute any value that represents a variable that is constant throughout the problem. No, we do not have anything that stays the same all the time in terms of a variable, not a rate, but a variable. Like the radius is not the same all the time. If that balloon is changing size, the radius is changing all the time, right? I don't have anything that's constant. Now, The other thing I want you to, dadgummit, the other thing I want you to highlight is what is here in italics. You can only have one more variable than you have rates. You can only have one more variable than you have rates. That's right. I only have one rate, so I can only have two variables in this thing. What are my variables? V and R. So I'm good. Now you may be thinking, what if you do have it where that doesn't apply? Then you got to do something different, and we'll get to a problem like that later. Now, number 5, implicitly differentiate both sides of the equation with respect to time. dv dt equals. Now we differentiated this one on the front page, if you remember. 4/3 pi is the coefficient. 4 dr dt. Well, partly. Let's look. Substitute in everything that you know. I know what dv dt is. Negative 230 pi. I know what r is. At the instant when r is 4. Now we're going to find dr dt. Yeah. So what do you have here? This is 64 pi dr dt equals negative 230 pi. So we're going to divide both sides by 64 pi. Oops. I don't want you going to your calculator unless it says to. You're going to write a sentence. What did you find? The radius of the balloon is changing, and let's not use the word changing. Is the radius of the balloon increasing or decreasing? So we're going to say something to the effect of the radius of the balloon is decreasing at a rate of 230 over 64 what? Cubic? 230 over 64 what? What's my unit? Radius. Centimeters. Radius is just a length. Centimeters. Centimeters per minute. The radius of the balloon is decreasing at a rate of 230 over 64 centimeters per minute when R is 4. And that's what I want you to say right there. You absolutely can write 115 over 32. This is a safe stop on a free response.
On our box answer, do we need to put like we have GR over TC?
As long as you label it in here, you're fine.
Okay.
But the label has to be somewhere. Yes.
Oh, yeah, sorry.
Oh, okay. Now, there's one mistake that I'm afraid you'll make because it's really, really a common mistake. What what students want to do is they want to say, oh, R is 4, so I'm going to substitute 4 in here I'm going to substitute 4 in here before I take the derivative. Mm-mm. Is the radius of that balloon always 4? No. Then you cannot substitute it in until after you take the derivative. Next page. You ever thrown rocks in a pond?
Yes.
Hasn't every kid thrown rocks in a pond? Can't make them skip. A stone is dropped into a body of calm water, causing ripples in the form of concentric circles. You know what concentric circles are? They have the same center. You know how you throw the rock in the pond and then so they all have the same center. There you go. There you go. All right. The radius of the outer ripple is increasing at a rate of 1 foot per second. Get your highlighter. The radius of the outer ripple is increasing at a rate of 1 foot per second. When the radius is 4 feet, at what rate is the total area of the disturbed water changing? Find, given, when. What do we want to find?
DADT.
That's right. Are you okay that I want to find DADT? I want to find DADT when R is 4, given DRDT equals 1. There you go. There you go. Makes sense so far? Charlotte? You good? Why are you on your calculator, dude? Okay. Just checking. Now we're going to write an equation. Well, what are we going to write an equation for? Area of a circle. They're not going to give you that one. What's the area of a circle? Please tell me it's pi r squared. Yes. How many variables do we have? 2. So how many, where is it? You can only have one more variable than you have rates. How many rates am I given? 1. How many variables do I have?
2.
Am I okay? Yes. Take the derivative with respect to time. DADT equals. That's it. 2 pi r dr dt, great. dr dt. Indeed. And an area is square units and a circumference is just units. Uh-huh. I mean, do you sometimes go, oh my gosh. Now, this is where we start plugging in. We know R, we know dr dt. So dA dt, 2 pi r, and I forgot what's dr dt. The radius is increasing, so that's positive. Yeah, you did. That's all right. Oh, sorry, R is 4. I knew there was something not right there. Let's see. I want to find dA dt when R is 4, given that dr dt is 1. All right. What do you get? What have we answered? What do we know now? The No, read. Rate, at what rate is the total area of the disturbed water changing? Answer the question using the words in the question. The total area of the disturbed water is, don't say changing, say increased or decreased. Increasing at a rate of, is it feet and seconds? Yes. Because there are a lot of different kinds of related rates problems. The total area of the disturbed water is increasing at a rate of 8 pi what? No. Area
So,
square feet per second, minute, was it second or minute?
second.
When, what was it, R is 4? Those units will cost you if you don't get those units right. Okay, are you doing okay?
So, whenever you write your sentence, you have to make sure that since we found area, you have to change the
You have to use the units that are appropriate for area. I love doing these. I really do. I like doing these problems. Okay. Highlighter. I feel like I'm a doctor in surgery. Scalpel. Okay. Highlighter. Syringe. Yeah. Water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. That's got to be important. If the radius of the tank is 4 feet, at what rate is the depth of the water changing? At any instant during the leak. Now, you notice it says at, I guess I ought to highlight that, at any instant. What are we trying to find? What is the, at what rate is the depth of the water changing? We'll just call that height. So what am I trying to find? dH/dt. So find dH/dt given, no, hang on. Water is leaking out of the cylindrical tank at a rate of 3 cubic feet per second. What am I given? What's -3? dV/dt. The volume, isn't the volume changing? What's the 4?
The radius equals 4. What? That's constant.
Because it's a cylindrical tank. Is the radius of the cylinder constant? Is it the same all the time? Yes. So I'm given that the radius is 4. The radius will not change.
So we get to
We have 2 givens. This Sparks liked R equals 4, didn't he? Please believe me, R is not always 4, all right? It just, yeah. Sparks thinks so. All right. I need an equation that relates volume and radius and height. Do you know what the formula for the volume of a cylinder is?
Pi r squared.
That's what it would happen to be. Pi r squared h. Again, that would be one that would be given to you. Volume equals pi r squared h. Now I'm going to ask you a question that's going to come back and answer exactly what Mary Grace just asked. She said on the sphere one, I told you you couldn't plug in the 4 for the radius because the radius was changing all the time. Can you plug in the r equals 4 here? Why can you?
Because it's constant.
Right. Now, other thing is, though, before you do that, look at your thing that I've had you highlight. You can only have one more variable than you have rates. How many variables do I have here in this problem? Right here, as it is. 3. How many rates am I given? 1. When you have a case like that, that means there's one of those variables that you're not going to be allowed to have in there. And in this case, it's because the radius is constant. So go ahead and substitute that in. We good? Now take the derivative with respect to time. I don't seem to know what that is. What's the derivative of 16 pi h with respect to time?
Equates 16 pi h dt.
Nope, there's nothing special about it. What's a uh-oh?
You know dv dt.
So dv dt is -3. And I hope I was looking for dh dt. Yep. So dh dt -3 over 16 pi. When you write your sentence, go back and use the wording from the problem. The depth of the water is changing. Remember, you don't have to use the word changing, we say increasing or decreasing. So the depth of the water, the depth of the water is decreasing. Now we're at depth, which is height. At a rate of, because I've already got the decreasing, I've taken care of the negative. 3 over 16 pi, and I don't remember my units. Feet per second at any instant. Go back and use the wording from the question. Feet per second at any instant. The AP graders will love you when you write stuff like that.
Oh, yay.
All right, let's see if we can get through one more before the bell. All right, here we go. Highlighter ready? A cone has a diameter of 10 inches and a height of 15 inches. So that's what the cone itself has a shape of. Not an ice cream cone, no. All right. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. And I'm going to put poured into so I'll remember if that's increasing or decreasing. It will be important, but it's not important for our find given when. It will be important in a little bit. All right. At the instant when the radius of the exposed surface area of the water is 2 inches, picture a cone, pointy part at the bottom. Water's in it. Can you see that the top is a circle?
Yes.
All right. At what rate is the volume of the water changing? Find dV dt. Given, what'd you say, d what? dH dt is 1.2. Positive because the height is increasing because water's being poured into it. When? Hey, he changed the R. All right, when R is 2.
Like a point.
What do you mean, kind of like a point?
Wait, never mind.
We need a formula for a what?
TV, DT.
Yeah, of a cone. And if you can't remember, look on the front page.
Fourth.
4/3?
Yeah.
1/3. Yeah. Volume is 1/3 pi r squared h. Now take a look. You can only have one more variable than you have rates. How many variables do we have? 3, V, R, and H. How many rates are we given? Snap.
They give you the radius, right? Because it's
They didn't give me dr dt or dv dt. They didn't give me dr dt. They didn't give me dv dt. They only gave me one rate. Okay? I got 3 variables. What's the most number of variables I can have? 2. That, Mason, is where this is going to come in. So, what you're going to do, you're going to go somewhere and you're going to draw yourself a cone. An upside down hat, yes. A dunce hat. A wizard.
yeah.
A wizard. Or a snow cone. The cone has a diameter of 10 inches and a height of 15 inches. Go radius. Did I teach you something? Did you just figure out something?
What?
All right. Explain what you just said to me, but explain it.
The length, the radius is 5 there, and the height is 15. We know the radius is 2 inches on the given statement. So we can say that 5
Is 2.
5 is to 15. So 2 is 2x. Since we solve it, it will be 15x would be 5 multiplied by 3.
So it had to be 6.
We're gonna set up a proportion, is what he's saying.
Oh.
30 equals 5x. So x would be 6.
Let's have a look.
6 divided 6.
Okay. Listen. I'll use blue. Okay. Now,
Couple of announcements before the bell rings.
now, keep in mind, what I've got to do is I got to figure out a way to get rid of a variable. The variable that I need h, because I'm given dH dt. So I need to keep H. I don't know crap about dr/dt, so I'm going to see if I can figure out a way to get rid of the r. So here's what I've got. 5 is to 15 as r is to h. You with me? 5 is to 15 as r is to h. But, let me see here. At the instant when, let me see here, blah, 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 when the radius of the exposed surface area of the water is 2 inches, so that'll be 2, right? Mm-hmm. So H is 6. Okay, hang on, there's something I want to look at real quick. That ain't it. Hang on a minute. Nope. Yeah. Now, but here's the thing. I can't put that in right away, can I? Because this is at the instant when R is 2, right? At the instant. So what I'm going to do is I'm going to go back here and I'm just going to write a little equation. I'm going to cross multiply. And if I cross multiply, I get 5H equals 15R. You with me? Which variable did I say I wanted to get rid of? I want to get rid of R. So let's make that say R equals. Do it real quick. If I make that say R equals, what's it going to be? 5H over 15, which is H over 3. What we're going to do Wednesday is pick up right there. Okay? Oops.